This is Lecture 1 for Module 9 in the book Problem Solving Guide for Mechanics and Thermodynamics. The subject is simple harmonic motion. Simple harmonic motion is rocking back and forth, in which the restoring force is proportional to the distance from the equilibrium point. So if we have a mass on a spring oscillating on a frictionless horizontal surface, it'll go back and forth, between the equilibrium point, the point where the spring is neither stretched nor compressed. And when the mass is on the right side of the equilibrium point, the force is back. And when the mass is on the left side, the force is back toward the middle. It's a restoring force. Further, it's proportional to the displacement. So as it goes further out, the restoring force gets bigger linearly. The force that's accelerating it back to the middle is proportional to the distance it is from the middle. An oscillating tuning fork is another example of simple harmonic motion. These are the two tines. As the tine gets farther and farther bent, the force restoring it gets bigger and bigger. In this module, we're going to investigate the parameters that describe simple harmonic motion: period, frequency, angular frequency, time, and the equation that connects them all. So one way to get the equation that describes the position of an object as a function of time is to use F equals ma. So we have a block oscillating on a spring on a horizontal surface right here. The force that it's exerted on it in the horizontal direction is only kx, so that's the only force in the x direction, and that's equal to ma. If you write the acceleration as the second derivative of the position with respect to time, we have this. That's ma. There's the force. The negative sign is because the acceleration is in the opposite direction as x. When x is positive, the acceleration is negative. When x is negative, the acceleration is positive. To solve this differential equation, you take the second derivative of something, x, and you get the same thing back times some constant. What function returns the negative of itself when two derivatives are taken? If you've taken a lot of derivatives, if you're experienced with derivatives, then you know the answer. It's sine and cosine. The derivative of sine x sine theta with respect to theta is cosine theta. The derivative of cosine theta with respect to theta is minus sine theta. So you start off at sine theta, you take two derivatives, and you get minus sine theta. That's the function. The most general solution to this equation is you put some constants in there. A, some constant in front, sine omega t plus delta. So A, omega, and delta are all constants. X is a function of time, and there's the t right there. Before we do anything else, let's check to see that this works. So we have this function x of t, A sine omega t plus delta. Let's plug it back into F equals ma, the differential equation we got from F equals ma, and make sure that it works. So we can see where it comes from. Here's F equals ma, with A written as the second derivative of the position with respect to time. The left-hand side's easy. The left-hand side is just kx, and x is A sine omega t plus delta. So I'm just writing down kx there. To get the right-hand side, we need to take two derivatives with respect to t. The first derivative of sine is cosine. You take the derivative of the angle, you get an omega. That comes out front. This is not a class in calculus. I'm going through this quickly. You take the second derivative. Now cosine becomes minus sine, and you pull out another omega. So now you got minus a omega squared. So this is the second derivative, and we can plug it back into this equation. So this is what we get. Kx equals minus m, second derivative of x with respect to time. There's an a sine omega t plus delta in both of these. They cancel out, leaving a k on this side and a plus m on this side and an omega squared. So we can solve this for omega squared. It's k over m. This equation is telling us a lot, but it's hard to figure out what it's telling us unless we know what the heck omega is. What's the physical meaning of omega? In the equation, our equation, it's in the angle. You're taking the sine of the angle. It's the variable part of the angle. Omega t, delta is just some constant. It's a phase shift. If you plug in t equals 0, then you get sine delta. So it's where the mass is at time equals 0. The changing thing is omega t. That's the thing we should pay attention to. It's the variable part of the angle, omega t. So we know that sine and cosine go through one complete cycle when the angle goes through 2 pi, 360 degrees, one cycle. The sine and cosine functions repeat after 2 pi, after one cycle. They do something and they do it again and again and again and again. And it repeats every 2 pi. The cosine of any angle theta is the same as that angle theta plus 360 degrees. It's just another cycle. We know that the angle is omega t plus delta, and we know that the sine and cosine repeat every 2 pi, every 360 degrees. So let's think about this starting at t equals 0. When is the first time after t equals 0 is the angle bigger by 2 pi? How long after t equals 0 is the angle bigger by 2 pi? At t equals 0, the angle's delta. The angle becomes 2 pi plus delta when omega t is 2 pi. So as soon as omega t grows to 2 pi, that's one cycle. It went through one cycle. The time it takes for one cycle is 2 pi over omega. We just solved this for t, the time for one cycle. We just put the omega on the other side. This is called the period, capital T, the time for one cycle. It's 2 pi over omega. So what the heck is omega? T is the period, big T. Omega is called the angular frequency. It has dimensions of angle per time. A common unit is radians per second, degrees per second, degrees per minute, revolutions per minute. The problem with revolutions per minute, when you put it in here and you multiply by t, you're going to have the angle in revolutions. And you're going to have to convert that in order to be able to use your calculator, because calculators have degrees and radians. If I ask you to take the cosine of a quarter of a revolution, you can do that by saying, well, a quarter of a revolution, 90 degrees. Cosine of 90 degrees is 0. But you don't have a button on your calculator for revolutions. But there's nothing wrong with having an omega in revolutions, except it might be hard to take the sine or cosine of it. We really have to understand what omega is, and we're going to keep going through some problems to make sure you get that understanding. So now we can go back to this. Omega squared is k over m. So omega is how many degrees per second, how many radians per second. This relates the angular frequency to the stiffness of the spring and the mass of the object that's oscillating, and this should make sense. Qualitative sense. With a high K, if you got a spring with a high stiffness, it's going to be oscillating faster. Right? Tuning forks, very stiff. If the mass that's going back is high, the frequency is going to be lower. It's hard to oscillate a high mass at a big frequency. So this equation makes sense. The bigger the mass, the smaller the frequency. The bigger the stiffness of the spring, the higher the frequency. A similar equation can be derived for the angular frequency of a pendulum oscillating at a small angle. So here's a pendulum that's going back and forth. What do you think the analogy is? Well, it's just, omega squared is g over L. The bigger the gravitational force, the higher the frequency. You can imagine doing this on Jupiter. It's going to be oscillating faster because Jupiter's pulling harder. On the moon, it's going to take a long time to go back and forth. And it's inversely proportional to the length. The longer the string, the shorter the frequency. Long strings have low frequency. So to test your understanding of angular frequency, let's try some problems. Tell me the period. I'm going to give you the angular frequency, and you're going to have to tell me the period. No equations. Equations are for people who can't think. Just let me know what it is because you understand angular frequency. Remember, to solve these, you can ask yourself, what time would make omega t 2 pi? Or 360 degrees, or one rotation? Because that's what the period is, the time it takes to undergo one cycle. Okay, omega is pi radians per second. Pi radians every second. You can pause it if you want. If it goes pi radians is half a cycle. If it goes half a cycle in 1 second, it takes 2 seconds to go one cycle. The period's 2 seconds. Just think about it. 2 pi radians every second. That's 1 cycle per second. The period is 1 second. 8 pi. It goes 8 pi. That's a lot. How many cycles is that? It's 4 cycles. If it goes 4 cycles in 1 second, the time it takes for one cycle is 1/4 of a second. The period is 1/4 of a second. 2,000 pi radians per second. Each cycle is 2 pi radians. So that's 1,000 cycles per second. If it goes 1,000 cycles per second, the period is 1,000th of a second. 1.001 seconds. 90 degrees per second. If it goes 90 degrees every second, how long does it take to get around? How long does it take to go 360 degrees? It's 4 seconds, right? 360 degrees per second. What's the period? It's 1 second. 3,600 degrees every second. That's 10 times around every second. The period is 1/10 of a second. 10 degrees per second. How long does that take to go around? 36 seconds, right? Has to go 360 degrees. 36 seconds to go all the way around. Half of a revolution per minute. If it goes half of a revolution in a minute, it takes 2 minutes to go a whole revolution. The period is 2 minutes. 1,000 rotations per second. 1,000 rotations per second means 1/1,000th of a second per rotation. The period is 1/1,000th of a second. Now let's talk about frequency. Not angular frequency, frequency. They're different. For some reason. Angular frequency gives the angle per time. Frequency gives cycle per time. The standard unit of frequency is the hertz, which is cycles per second. 10 hertz is 10 cycles per second. The symbol for frequency is F. The period T has units of seconds for one cycle. That's the period, the definition of the period, the seconds, the time per one cycle. The frequency, which has units of cycles per second, is the inverse of the period, which has seconds per cycle. So, let's think about a tuning fork. It's got a frequency of 5,000 hertz. If it has a frequency of 5,000 hertz, it makes 5,000 complete vibrations every second. That's what a hertz is. What's the period of a tuning fork that has a frequency of 5,000 hertz? It's got to be 1/500th of a second. If it goes back and forth 500 times every second, each vibration has to take 1/500th of a second, right? Makes sense. Here's a slightly tougher question. Slightly. If the frequency is 5,000 hertz, what's the angular frequency? There's a couple of different ways to express it. You have to give it to me in angle per time. 500 cycles per second, what's the angular frequency? So there's our tuning fork. What's omega? There are 2 pi radians in one cycle. So there are 1,000 pi radians in 500 cycles. The angular frequency is 1,000 pi radians per second, or if you like, 3,146 radians per second. If you want, you can give it to me in degrees. There's 360 degrees in one cycle, 180,000 degrees in 500 cycles. So the angular frequency is 180,000 degrees every second. It's important to be able to get omegas because the omega is the thing that goes in front of the t in the angle, in the equation. In this equation, you need an omega. And the omega is going to be some angle per time. And when you multiply the time units are going to cancel. They should be the same, of course, seconds, minutes, whatever. And you're going to be left with an angle. And you're going to be taking the sine of that angle. And you can take the sine of things in degrees or radians with your calculator. So whatever you're more familiar with, you can do. Basically, there's 3 different ways to describe something that's undergoing simple harmonic motion. You can just describe it in words. So here's an example. Pendulum starts at x equals 0, at t equals 0, and oscillates back and forth with a frequency of 0.3 hertz and an amplitude of 20 centimeters. So we're describing the motion. The second is with an equation. X of t is 20 centimeters sine 1.885 radians per second t. That's an equation. The third is with the graph. Here's the motion. Tell me what the frequency is. Tell me what the period is. Tell me what the amplitude is. What is the equation given the graph? So you should be able to get the other 2 with any of those 3. All of these 3 descriptions here are used for examples, describe exactly the same motion. 3 different ways to describe the same motion. The first one says, look, the frequency is 0.3 hertz. If it's 0.3 hertz, what's the period? 0.3 cycles per second. So it takes 3 1/3 seconds to get up to 1 cycle, right? If it's 0.3 cycles per second, we can just take our calculator and go 1 over 0.3, and it tells us the period is 3.33 seconds. So it takes 3.33 seconds to go through 1 cycle. And we can see on the graph, that's about 3.33 seconds. With a period of 3.33 seconds, it will make 3 complete oscillations in 10 seconds. 3.33 seconds per oscillation. So there's 1 oscillation, there's 2 oscillations, there's 3 oscillations, and there's 10 seconds. 3 cycles, 10 seconds. Should all make sense. We can also calculate that 0.3 of 2 pi. 2 pi is about 6.28, right? 0.3 of that is 1.885 radians. So 0.3 cycles per second is the same as 1.885 radians per second. We converted the frequency to an angular frequency. So now when we plug in the time here and we multiply that by 1.885 radians per second, we're going to get an angle in radians, and we can take the sine of that with our calculator. We're going to multiply by 20, and we're going to find a point on this graph. In fact, you should probably do that. Plug in 12 seconds. 12 seconds should be about right here. What does it look like to you? 12 seconds should be minus 12? Minus 12 centimeters, something like that. Somewhere down here. Try a few t's and see that they match this graph. This graph is that function, and it is this description. So here's a sample exam question. Cicadas produce their steady droning chirp that you hear once every 17 years with their timbal. It's right here. It's a membrane with ribs. They buckle against each other hundreds of times every second, and they make that. So let's assume that a motion of this rib, one of these ribs, is simple harmonic, which is probably a bad assumption, but it's okay. We're doing physics. So write the equation of motion for one rib, oscillating at a frequency of 400 hertz with an amplitude of 100 microns. What's the equation of motion? Well, it says assume that the rib is at plus 100 microns at t equals 0. What does that tell us? We know the amplitude is 100 microns. It's given. We know that we're going to use the cosine function because cosine is a maximum at t equals 0. We could also do it with the phase shift, but we're just going to change the function to cosine. Cosine of 0 is 1. So now we only need the angular frequency. That's our last parameter. And you might want to pause it and see if you can figure out what omega is. The frequency is 400 hertz. 400 cycles every second. If it goes 400 cycles every second, how many radians does it go every second? 400 cycles is 800 pi radians because each cycle is 2 pi radians. So there's the equation. X of t is 100 microns, cosine 800 pi radians per second t. When I plug in t equals 0, I get 0 for the angle. Cosine of 0 is 1. I multiply 1 by 100 microns, and I get 100 microns, and it says that the rib is at 1 plus 100 microns at t equals 0, and that's what this equation gives us. There's a question for you. How long will it take this angle to go from 0 to 2 pi? We know it starts at 0. When I plug in 0, I get 0 for the angle. When is the first time? When is this angle 2 pi? When is the number in square brackets equal to 2 pi? 800 pi, t's got to be 1/400th. If t is 1/400th of a second, then we have the angle. 800 divided by 400 is 2. And we have 2 pi. The angle is 2 pi radians. And that's the period, right? The period is 1/400th of a second because it goes 400 cycles every second. When I put in 1/400th of a second, I get 2 pi radians as the angle. This should all make sense eventually. If it doesn't make sense now, you need to do a lot of problems. Finally, here's the plot. What is 1/400th of a second? If you take your calculator and you go 400 1 over x, what is it? 1 divided by 400. 1/400th should be 0.0025. 0.0025. So here's a plot of the motion. Displacement in microns, time in seconds. Starts off at 100 microns. That's a cosine. Comes down here, goes back up here. This is one cycle right here. 0.0025. That's the period, 0.0025 seconds. And we can see that that's 1/400th of a second right there. So all of this should make sense eventually. And the way for it to make sense is to do a lot of problems. Get going.